is Dr. Lionel Hirschberg. He will be talking about sound production due to essentially unsteady and quasi-steady nozzle interactions with a focus on the main flow-oriented vorticity noise. I hope I spelled it correctly. The letter is just too small for me. But please, Lionel, go ahead. It's a great honor to have you with us. It's, you and I have a kind of a long story behind us, and this is curious to be having here. Without further ado, please go ahead and welcome to the seminar.
Thank you very much, Enrique. I changed the title of my presentation a little bit, but I'm basically going to talk to you guys about the contributions about my contributions and my co-authors' contributions to the understanding of what we call vorticity noise in a jargon. This is relevant for indirect combustion noise problems in solid rocket motors and aircraft engines. Now, what do we mean by vorticity noise? I think it's most expedient to just start by way of example to explain what we mean by that. And for that, let's turn to Ariane 5, the launch vehicle, which was the subject of my PhD thesis. In it, there are problems, more specifically in the solid rocket motor boosters that are highlighted by the red rectangles on this slide of self-sustained pressure pulsations. And so I turned my attention to the study of these systems. And the solid rocket motor is actually quite simple device. Seem to have a problem. Okay. Sorry, thank you for bearing with me. So a solid rocket motor is actually a pretty simple device. I show a sketch on this slide. It's basically a cylindrical tube closed at the head end with a nozzle downstream. So that's the combustion chamber exit. And on the side walls, there are basically propellant grains, and those are a mix of oxidizer and fuel that are separated by turbo inhibitors. And once you ignite this propellant, it causes, the combustion basically causes a mass flow that exits through the nozzle. And this nozzle is basically a convergent divergent. And at the point where the cross-sectional surface area is the smallest, we call this area the nozzle throat. And the conditions inside of this combustion chamber, they're such that the static pressure is about 5 megapascals. And that means that at the nozzle throat, the Mach number based on the actual velocity, ux throat, divided by the speed, local speed of sound equals 1. We say that the flow is transonic, and we call this a choked nozzle flow. There are some characteristics of the acoustics of this system that I want to explain to you. So basically, there are strong acoustic reflections at the up and downstream ends of this cylindrical tube. So qualitatively, we can model this as a closed pipe system for the sake of acoustics. And the lowest longitudinal acoustic mode, which we call the first longitudinal acoustic mode that you have in this system, is a half a wavelength. What I'm showing on this slide is basically measurements of actual real flight. And what you see are the pulsation amplitude in megapascals as a function of flight time. And the black line indicates the lowest longitudinal acoustic mode. That is the half a wavelength that I referred to earlier. And what you see is that halfway through flight of these boosters attached to the main stage is about 2 minutes. And 1 minute into flight, you have the occurrence of these strong pressure pulsations. The amplitude of these pulsations with respect to the static pressure in the chamber is about 4 times 10 to the power minus 3. So you have a problem. A minute after takeoff, you have these spurious self-sustained pressure pulsations. And in terms of force, they represent about 3,000 kilonewtons. Why is this a problem? Well, that's because the whole design purpose of Ariane 5 and launch vehicles like it is to bring payload, i.e. satellites, into stationary orbit around the Earth. These are very, very expensive devices. They cost about $1 billion US to make, basically. And they're fragile. So you want them to arrive into our outer orbit or orbit around the Earth, and you want them to work. The problem is that you have these self-sustained pressure pulsations that occur, and if in the worst case scenario, this can cause vibrations that couple with the structure of the main stage and pose a threat to the payload. So it becomes imperative to understand what fundamentally drives these self-sustained pressure pulsations. And the sound source especially is important, and that was the focus of my PhD thesis. So let's turn again to the occurrence of these pressure pulsations in these solid rocket motors. So we have the pulsation amplitude in megapascals as a function of flight time in seconds, and we observe that they only start to occur halfway through flight. And you can legitimately ask yourself, why would this be? And as it happens, there are two components to this answer. The first is that this propellant grain that I talked about earlier is separated by thermal inhibitors. And as the propellant grain burns, these thermal inhibitors protrude out of the burning surface, and you have vortex shedding on these thermal inhibitors, and ring vortices are created that convect downstream with the base flow, have an interaction with the combustion chamber exit. So that's what I'm showing here. This is a numerical simulation performed by Jérôme Antoine, who did a PhD thesis in the 1990s on this subject. And basically, my work builds on what he has done, or our work, me and my co-authors. So you have vortex shedding at these thermal inhibitors, and these ring vortices convect downstream and have an interaction with the combustion chamber, that is the choke nozzle. So the combustion chamber exit. Another thing that happens is that the type of nozzle that is used in these systems is what you call an integrated nozzle. That means that there is a volume around the inlet of this convergent divergent nozzle. And initially, that is the first 60 seconds approximately, this whole volume is filled with propellant. But as flight progresses, this propellant burns, and you now have an acoustically available cavity volume, a volume VC. Well, Jérôme Antoine experimentally established that the pressure pulsations in these systems is proportional to this cavity volume VC. And me and my co-authors, by doing systematic numerical investigations, were able to confirm this and derive scaling laws. These numerical investigations, I've done them using a state-of-the-art area acoustics code developed by Stephen J. Hulshoff of the Delft University of Technology. And on this slide, I show an example of such a simulation where the nozzle is a simple nozzle that is without these nozzle cavities. And you will see it already, there's an effect. So for this simulation, we established a steady base flow that goes from left to right on this slide, and is such that the combustion chamber exit, the nozzle, is choked. That is, at the nozzle throat, you have a local actual Mach number of 1. Upstream from this choked nozzle, we generate a ring vortex. And the color scheme on this slide indicates a normalized pressure. So we have a mature ring vortex that is generated upstream from the choke nozzle, and it will convect downstream with a steady base flow. And on approach to the nozzle, it will start to have an interaction which continues as the ring is being ingested by the choke nozzle. And this interaction causes a plane acoustic wave to be created and to travel back upstream. Me and my co-authors referred to this as ring vortex nozzle interaction. So you have a situation where vortices are shed upstream from a choke nozzle. There's a convective delay. You have this ring vortex nozzle interaction, which produces an acoustic wave that travels back upstream, which causes vortex shedding in these systems. So you have a feedback loop, and as such, this is a self-sustained pressure pulsation. So our contribution was to derive scaling laws for sound production due to ring vortex nozzle interaction, and we developed analytical models. So in this system, sound is being produced by, basically the sound source in this system is the unsteady hydrodynamic reaction force from the nozzle inlet walls on the fluid. And the force is a time-dependent force which is being induced by the ring vortex as it approaches the nozzle and is being ingested by it. So the sound source here, we've called it ring vortex nozzle interaction. In the literature, in the jargon, one refers to this as indirect combustion noise because the propellant is burning and this causes the mass flow and the shedding of the vortices, etc. Another term for this specific type of indirect combustion noise is called vorticity noise. That's what people refer to it in the literature. So the important thing here is that in the system, the type of vortices that are created are ring vortices. And I have a very nice picture on this slide that shows a ring vortex. The most important takeaway from this picture is that you can clearly see that the vorticity component is normal to the main flow for ring vortices. But vorticity is a vortex, or is a, vorticity is a vector. And as such, you can always decompose a vector. And I propose that we decompose it in a component that is normal to the actual or main flow direction, and one that is parallel to the main flow direction. So contributions to vorticity noise due to the normal component, that would be ring vortex nozzle interaction, for example, and that was the subject of my PhD. Everything that is parallel to the main flow or parallel to the actual flow direction, that's what we would call swill nozzle interaction or actual vortex nozzle interaction. And that was the subject of my investigations during my postdoc at the DLR in Berlin, where I worked in Friedrich Bahnke's group. And they are interested in noise, indirect combustion noise produced in civil aviation aircraft engines. And on this slide, I show a sketch of such an engine. So you have a compressor, a combustor, and a turbine. And it's in the combustor that things happen that are of interest for the DLR, at least that team. So that's highlighted by the red rectangle on this slide. And what's important to note is that upstream from basically the combustor inlet, there's a device called a swirler. And this swirler, what it does, it creates an actually oriented vortex, or what they call a swirl, to stabilize combustion. So the reacting zone is basically has an actually oriented vortex, or a vortex that is in the direction of the main flow. So you have a vorticity component that is in the parallel to the main flow direction. But when you take a step back and you look at such a combustor, and I show a very simple sketch of the combustor here, you have an upstream swirler, which causes a swirl that is an actual vortex to be created. So you have a vorticity component in the direction of the main flow, and this will obviously have an interaction with the combustion chamber exit, and that's a turbine stage. Well, a turbine stage, it's basically a succession of rows of choked nozzles. It is extremely expensive and complicated to do either numerical simulations or experiments with rotating machines. So at the DLR, they chose to simplify. And they have a setup there that I helped to improve, where you basically investigate the interaction of swirl or actual vorticity with a choke nozzle with a single choke nozzle. And on this slide, I show the upstream part of this experimental setup. But it's more it's easier to understand what we did if you look at the sketch that I show on this slide. So you have a mass flow rate that we impose upstream. So that's on the left-hand side highlighted by the red rectangle, M1 dot, which we impose, and it is 43 kilogram hours, and it imposes basically a steady base flow that goes from left to right and goes through a convergent divergent nozzle, and is such that the nozzle is choked. That is, at the nozzle throat, we have an actual Mach number equal 1, and we chose 43 kilogram hours because we have a choked nozzle flow, but the downstream shock is weak. So you have a normal shock that exists downstream from this nozzle throat. So you have this steady base flow. A little note about the notation on this slide. Basically, the subscript 1 indicates parameters upstream from the nozzle, and the subscript 2 indicates parameters or variables that are downstream from the choke nozzle. So basically, we have a situation where we've imposed a steady base flow. You have a choked nozzle, and we are now going to do tangential injections of air from a pressurized reservoir in the region that I highlight with the red rectangle on this slide. We do this using an unsteady tangential injection module, which I show on this slide. The most important part of this injection module is a fast switching valve. It's basically a valve that opens and closes very quickly in 2 milliseconds. You can fix the time that the valve is open, and we've done this. So for example, in the results that I'm about to show you, we fixed it at 24 milliseconds. And what we did in the experiment is basically open this for 24 milliseconds, then wait 3 seconds, and then redo an injection event, and basically repeat this 100 times, and then average the signal to get rid of some noise. So upstream, we generate an actually oriented vortex structure or a swirl structure. This will interact with the choke nozzle, and this will cause a acoustic response, which we can measure in the downstream pipe section. So that's in the area highlighted by the red rectangle on this slide. The distance between the microphone that we use to record this acoustic response and basically the end of the experimental setup is 24 meters, or it was. And we've chosen this very long pipe section because it allows us to measure the acoustic signal without upstream traveling acoustic reflections. So we have basically an anechoic signal for about 140 milliseconds. What I show on this slide is an example of an acoustic response for an opening time of 24 milliseconds. So on the vertical axis, you have P2 prime in pascals, the downstream acoustic signal, as a function of measurement time in seconds on the horizontal axis. And basically, as it turns out, after our analysis, we find that this response due to the interaction of swill with this choke nozzle occurs in 3 steps. The first step is an ingestion phase. This causes an abrupt decrease of pressure in the downstream pipe section. Then we have the presence of swill in the nozzle, which causes a plateau. And then you have a rapid increase of pressure in the downstream pipe section, and that's due to the evacuation of said swill. So you might ask yourself, why would that be? And that's a very legitimate question. I'm going to attempt to qualitatively answer this question for the ingestion phase. So consider the convergent divergent nozzle. And we impose upstream, we impose a mass flow rate, m dot, which is basically causes a quasi-1D flow. And it is such that at the nozzle throat, we have a Mach number based on the actual flow velocity, ux at the throat, and the local speed of sound, the Mach number based on these equals 1. The most important consequence of this choking condition is that basically any perturbations that occur downstream from the nozzle throat cannot travel back upstream. Imagine now if we introduce a swill structure upstream from the choke nozzle, as shown on this slide. Initially, there is no swill or actually oriented vortex at the nozzle throat. So there is no azimuthal velocity component. But then it will get to the nozzle throat and will ingest this swill, and this will cause a very significant stretching, and it will cause an azimuthal velocity component to exist at the nozzle throat. So the choking condition will remain the same, but the Mach number is now a Mach number that is basically the sum of the actual Mach number at the throat squared plus the azimuthal Mach number at the throat squared, and you take the square root of that. So basically you have a situation where swill goes into the nozzle, which causes significant axial stretching. This causes an increase in rotational energy, and because of energy conservation, this causes a reduction of actual mass flow rate. So these types of problems have been studied since the 1970s, and famous papers by Carpenter, but for steady flow, right? Whereas the experience that we did is an unsteady tangential injection event. Now, consider the formula that I show on this slide. It says that the change in actual mass flow rate due to the presence of swill at the throat with respect to the swill-free case is proportional to the Mach number, azimuthal Mach number at the nozzle throat squared. So this means that when you have swill at the throat, the actual mass flow rate reduces. So what we can do then is use this information to propose a simple acoustic model for the downstream acoustic response, where we assume that we basically have a semi-infinite system. There's no acoustic reflections that travel back upstream. And we find that the acoustic response downstream, delta P2 prime, is approximately equal to the speed of sound in the downstream pipe section divided by the cross-sectional surface area of said pipe times the actual mass flow rate change, delta m dot. And delta m dot is negative when the swill structure is ingested. It is 0 when the swill is present, so you have a plateau. And then it is positive when the swill is being evacuated by the choke nozzle. So we asked ourselves, is this a quasi-steady mechanism? And the reason why we asked ourselves this question is that there's a plateau. Moreover, we did experiments where we lowered and augmented the opening time of this fast switching valve, and we found that the acoustic response was not affected by the injection time. So we thought it would be worth trying coming up with a quasi-steady model. And to do that, we replaced in the experiment the unsteady injection valve with a mass flow controller, such that we could fix the tangential mass flow rate m theta dot steady and this actual mass flow rate m1 dot. And we did it such that the total would remain those 43 kilogram hours. So we could vary the ratio between the steady tangential mass flow rate m theta dot steady divided by m dot, or divided by 43 kilogram hours. But we did, whenever we changed basically this ratio, we would wait 5 minutes for steady flow to establish, and then measure the upstream reservoir pressure P1 steady using a barometric manometer. And the results are shown on this slide. So you have on the vertical axis, the steady upstream reservoir pressure in pascals as a function of the ratio of the steady tangential mass flow rate divided by 43 kilogram hours, and this is squared. So what can you do with this information? Well, you can look, for example, at the horizontal axis and look at 0.14 and see that due to the presence of a vortex with this intensity, so to speak, it causes the upstream reservoir pressure to increase by an amount of delta P1 steady. Now, these data, we have them for a number of points, and we substitute them in a quasi-steady model, which we derive in an upcoming internoise paper, and which is also treated in a recently published Journal of Sound and Vibration paper that I'll happily share with you all. So moving on, let's return to the acoustic measurement. So if you recall, you have basically a lowering of the pressure due to swirl ingestion and an increase in downstream pressure due to the evacuation of said swirl. And we notice that the amplitudes are smaller for swirl ingestion and larger for swirl evacuation. So in what follows, delta P2 prime is scaled, and I've done this by multiplying by the density in the downstream pipe section times the cross-sectional surface area squared of the downstream pipe section divided by the unsteady tangential mass flow rate injected upstream m theta dot squared. And the result is shown on this slide. So you have this downstream acoustic response, dimensionless acoustic response, as a function of the ratio of the unsteady tangential mass flow rate, m theta dot, divided by those 43 kilogram hours, and that's squared. The most important first thing that you observe is that you basically have two horizontal lines. The crosses here are the amplitudes due to swirl ingestion, and the circles are due to swirl evacuation. And you see basically there's two horizontal lines, and we see about a 40% systematic deviation in amplitude due to swirl evacuation and swirl ingestion. But more importantly, because these are horizontal lines, this confirms that the downstream acoustic response, delta P2 prime, is proportional to the upstream injected tangential mass flow rate squared. And this means that it's also proportional to the Mach number, the azimuthal Mach number at the nozzle throat squared. So this confirms quasi-steady behavior. On this slide, I compare the experimental data to our quasi-steady model, again, which is described in our GSV paper, and indicated with the stars connected by the finely dotted line on this slide. And as you can see, there's a quite good agreement between the data for swirl evacuation and our model. So I conclude, we've measured the acoustic response downstream from a choke nozzle due to swirl ingestion and evacuation. We find that there's a systematic difference in amplitude between those of about 40%. And we find that the acoustic response scales quadratically with the upstream injected unsteady mass flow rate squared. Swirl evacuation those data compare very well with a quasi-steady model that we have proposed. And as such, to me, this confirms the pertinence of quasi-steady modeling for this experiment. Now, before I leave you, I just want to leave you with some general remarks on vorticity noise, that is indirect combustion noise due to vortices and vorticity as you can find them in the literature. If you look at the literature, you will find that most models are based on linear theory. But in our experiment, those swirl effects, they're quadratic. Moreover, in the literature, you will find that vorticity is being treated as a scalar, but vorticity is obviously a vector. And you also find basically bare assertions that somehow the sound source in these systems, this indirect noise, is due to the acceleration of vorticity, or what they call vorticity waves. This is obviously not the case in the experiment that we've performed at the DLR. As such, it is my position that the vorticity noise paradigm, as it relates to indirect combustion noise, should be reconsidered. I would like to acknowledge the folks that funded this research. So that's the NFT and the German Academic Exchange Service. But more importantly, I want to acknowledge my co-authors, Steve Hulshoff, Friedrich Bake, Karsten Knobloch, Angelo Ridolfi, Sebastian Krug, Olivier Klose, Thierry Schuler, Christophe Schramm, Jean Collinet, and Avram Hirschberg. I would also like to thank Amy Morgans, my boss, who has allowed me to do some of the analysis that I've presented here while I was working in her group. And I will be forever grateful for that. So thank you all for inviting me to speak, and thank you for your attention.
Lionel, for this very nice presentation, very interesting topic. So perhaps we have time for just one short question due to the time. I don't know if there is any questions. Everyone in the room would like to ask anything? Well, I may have one question, Lionel. So what's the countermeasure? Do you envisage any kind of countermeasure to avoid having these unstable modes due to vortex shedding that create these pressure pulsations in the nozzles?
Well, I mean, it depends. You mean as it relates to those solid rocket motor boosters?
Yes, perhaps. Why not? Yeah.
Yes. I think the easiest countermeasure is to not have nozzle cavity volume, basically. If VC is very small, basically, if VC is 0, or you will always have basically if they would just not use an integrated nozzle, you would not have the onset of this acoustically evadable, this acoustically evadable cavity volume halfway through flight. And this would, hold on, can you see this? If you would just have a nozzle that does not have a cavity around it, like is shown on this slide, you would basically suppress the most, orders of magnitude of pulsations. So that's a passive countermeasure that you can have. But because of the design, and I suppose that they basically also used the fact that those nozzles are integrated for other things, therefore for some reason these have not been phased out. So, but that would be a very easy way to suppress these self-sustained pressure pulsations in this system.
Thank you very much.
You're welcome.
I don't know if there's any question. No questions. Okay, well, I hope we will see more about your work in the upcoming events. I will invite you to the Congress of the Fluid Dynamics Division.
Right, thank you.
And have more opportunity to interact with you. Thank you very much, Lionel. It's been great to have you with us.
Thanks for inviting me, Enrique. And if anybody wants, my most recent paper, the GSV paper, or I should say mine and my co-authors, is basically open access, so anybody with an internet connection can find it. So a cursory Google search will allow you to find our paper. So feel free to go check it out. Right. So anyway.
Thank you so much, man.
Thank you. I'll stop sharing now. Thank you all. Bye.
Bye-bye. So